I'm going to be pretty quick with proposition 8 because the techniques are the same as propositions 6, 7, 5, 4, so it's a bit boring. So I'll make the statement and then just kind of skip over the things that are automatic at this point. If a straight line be cut at some point, so our straight line is actually reevaluate that, AB, and if we cut it at C, so that's C, 4 times the rectangle contained by the hole in one of the segments so the hole is AB. One of the segments, well, it means we could choose AC or BC, but we'll choose BC. So 4 times the rectangle, so this rectangle means AB, sort of product with BC, together with the square on the remaining segment, which is AC. Is equal to the square on the hole and the aforesaid segment as on one straight line. So what it means is that if I continued this line by a segment equal in length to BC, so I'm going to call this D, so it's the square on, and then the line on which the square is described, and the line on which the square is described is the hole together with the segment BC. I can't wait to see what Euclid is going to do when aforesaid can't work, like when there's more than one thing in the statement. Some like desperate wriggling to avoid introducing rotation for things.
Yes.
Okay, so let's start constructing. So we know we can extend AB by a length equal to BC to get AD. And then we know we can construct a square on AD. So let me draw that. And then we can draw this diagonal. And then we can drop lines. A line passing through B perpendicular to, these are E and F. So we can make lines, parallel rather, to DF passing through B and passing through C. And we can similarly, if I call that K and that Q, I can draw a line parallel to AD passing through K and a line through here passing through Q. And I'm going to name these N, P, R, G. M, and O. All right, so here's the rapid fire bit. So proof. I'm just going to say the squares indicated with this blue notation, namely CK, BN, GR, and KP, are all equal. This we proved by techniques we're familiar with by now. The rectangles indicated with a red corner are also all equal. This ultimately, again, this is a familiar technique. Maybe I'll comment on AG and RF. So that's the only part I'll spell out in some detail. So AG is, maybe I'll say AG is equal to MQ. That's because CG is equal to GQ for reasons we've sort of addressed before, and they have a common base AC, or rather AC is equal to MG. Okay, so that gives us that AG is equal to MQ. Now it's, which proposition? 1.43. Well, and similarly, QL equals RF, and by proposition 1.43, MQ equals QL. Right, that's because they're, whatever the terminology was, complements of the parallelogram ML. Right, if I look back over on this diagram here, I've got the parallelogram ML, and these two parallelograms, or rectangles, are complements, and complements are equal. So that gives us that all four of these rectangles are equal to one another, and in particular to AG. Okay, so I'm just going to, that's kind of half the proof, but it's routine for us at this point. So now let me continue from there. Let's see. The 8 areas which contain the gnomon STU, which I'll now indicate. All right, so that's the gnomon STU. So I hope it's clear which areas I mean, right? Those 8 regions that have just been colored in. Well, so it's clear if we count them up that we get, so if we look at the area AK, which is one of the reds plus one of the blues, if you take 4 times that, you have 4 reds and 4 blues. So that's the gnomon STU. So the 8 areas which contain the gnomon STU are quadruple AK. Therefore, 4 times the rectangle AB, BD. Because by construction, well, maybe not by construction, but we deduced in the part that I didn't go through that BD is equal to BK. So the rectangle AK is the rectangle on AB and BD. Let OH be added to both, and we're done. Right? Because remember, the claim was that the square on the whole would be equal to 4 times AB. Well, I said BC, but that's the same as BD. Would be 4 times that rectangle plus the square on the remaining segment, which was AC, which is what OH is. So that's it. All right, I'll pass control over to you, Ken.
Cool, thanks, Dan. Let's see if I can finish the next one in 15 minutes. Probably not. Might go. Let's move over to the next board. Let's move right over so we get 2 boards. Okay. So proposition 2.9 is slightly different to the previous ones. It's maybe the identity that that we get is something that you recognize. So if a straight recognized, as in you may have even used it, is cut into unequal pieces, and as before, I'm gonna make the construction as I go. So maybe the diagram like this. So this is my straight line, AB. I cut it into unequal pieces, like that. Then the sum of squares on the unequal pieces so that's just well, I haven't labeled this point yet. I'm going to call it D. I'm reserving C for something else. So this is AD cross AD plus DB cross DB. If we want to use notation, is double the sum of the square on half the line so that's why I reserve C. I want C to be midpoint, so C is half the line. The last term is a bit of a mouthful. Sum of the square and half line and the difference between the equal and unequal pieces. The equal and unequal pieces. So that is to say, AD minus AC. So let's actually do this. So let's call this length A and call this length B. I know I probably should put arrows to indicate what I'm doing. B. Then what this says algebraically is going back the sum of the squares on the unequal pieces, so that's just going to be A squared plus B squared, and that's equal to twice the this part is double the sum of the square and half the line, so square and half the line is a plus b on 2 squared. And the difference between the equal and unequal pieces will be, I guess, a plus b on 2 all squared minus b squared. Sorry, not the square, so not there. Erase these. You want the square on that difference. Okay, so you recognize this as a squared plus a plus b squared plus a minus b squared, and that's equal to a, twice of, I guess not twice, a squared plus b squared if you get rid of all the coefficients. So you definitely would have seen this one before. And the construction that goes into proving this goes as follows. So I'll do the construction next. So there's a statement is there. The construction goes like this. So we're gonna put a line from C that's perpendicular to AB of the same length as AC. So the various propositions that allow us to do this. These are propositions 1.11 and 1.3. So proposition 1.11 lets us construct this perpendicular line. Gives us a line or maybe I should say, maybe I shouldn't say perpendicular because it's not one of Euclid's words. Line at C at right angles to AB. And proposition 1.3 allows us to give this line segment the same length. I'll just write same length. And so this is point E then. And we're just going to join up the rest of these points that we've created. And the next construction should be familiar to us. We've done this a few times previous to today. We're going to draw a line from D that's parallel to the one we just constructed, which is CE. We call this point F. And this is a parallel, so I'll mark it as parallel. And you probably even know the proposition by now. It's proposition 1.31. And we're going to do the same thing here. I'm going to do the same thing here. Constructive line parallel to AB now from F, and that hits CE at G. And draw little arrows there. And so proposition 1.3 allows us to construct this line and this line there. Okay, so here are our constructions, and I'll do the proof on the next board. Okay. So proof. So the proof goes like this. Since AC is equal to CE, so AC is half the line. CE is the one we constructed to be equal to half the line. The angles EAC and AEC are equal. And this is due to proposition 1.5. Proposition about triangles. So the two angles we're talking about are these ones. Actually, there's one more thing I forgot to do on this diagram. Let's join up this line here. We're going to use this line a little bit later in the proof, but let's draw it in for now. So EAC and AEC are equal, the two angles marked in green. And since ECA is a right angle, again by construction, that's a right angle. EAC and AEC are both equal to half right angle. This follows from proposition 1.32, which says that the angle sum of triangles is equal to two right angles. A fact that we're all familiar with. We'll call it 180 degrees usually, the two right angles. And so we've got these two. And similarly, we're going to apply the same argument to the other side. We've cut this line AB into two with a perpendicular line at C, right? So we've got basically the mirror on the other side. So similarly, we get CBE and CEB are both equal to half right angles. Essentially the same argument. So I'll just mark these as the same. So they're actually all the same, right? They're all equal to half a right angle. Okay. So AEB. So the conclusion here we want to draw here is that AEB is actually a right angle. So this is just because AEB is a sum of two half right angles. So I'll mark this one in as well. All right, this is a right angle here. Hence, AEB is a right angle. Okay. Okay, so next we're going to appeal to proposition 1.29. Which says that the angles ACE, CBE, and GFE are equal. In fact, they're both equal to half a right angle as well. Equal, and in fact, and both equal to half a right angle. I'll go back to the diagram, CBE and GFE. CBE is this one, GFE is this one, right? So proposition 1.29 says that we've got parallel lines and you've got, whatever these are called, opposite internal angles. Then they're equal. And both equal to half a right angle, because all the angles we're talking about are equal to half a right angle, conveniently. So that's good. And so GFE, this is angle GFE, is equal to GEF, right? And by proposition 1.6, EG is equal to GF. Okay, so going back to the diagram, EG is here. This is this line. GF is this line. We've shown that two of the angles in this triangle equals must be an isosceles triangle, and that's 1.6. And we can make a similar argument to show that FD and DB are the same. So I'll use a different color now because these are not necessarily the same as GE and GF, but these are the same, right? So similarly, FD is equal to DB. Okay, so essentially the same argument applied to the little triangle on the right, and there's the one we did on top of well, EGF and FDB. Same argument. Okay, so I think from this point on, sorry, I try to scroll the screen. So from this point on, it's mostly algebra using Pythagoras' theorem. So we've done some geometrical arguments using the techniques from, we've seen some of these from chapter 1, book 1. We haven't seen this in a while. But now we're going to switch gears and do a bunch of algebraic type manipulations. So so this is going to be a slightly different flavor. So since AC is equal to CE, right? So this is the first hypothesis that we went with. We're going back to it. We're going to say that the squares AC cross AC is equal to CE cross CE. This is not a surprise. And I'm going to have to go to the next board, and hopefully we won't forget. It's not too bad. Yeah, so AC cross AC plus CE cross CE. So now we're going to be doing. Okay, so now I'm not doing anything. I'm not doing anything profound. I'm just writing down a bunch of things that are obvious, right? They're the same. We add them together. You should get twice the first term. That's all we're doing here. So let's hop over to the next board and finish off the proof. I'm going to use Pythagoras at some point. Okay. Good. So we haven't written down anything super profound, and now we're going to use Pythagoras. And EA cross EA is equal to AC cross AC plus CE cross CE. So if you remember, EA was the hypotenuse that we drew, AC was the base, and CE was a line that we drew vertical, right? And so these are all squares, so this is essentially just Pythagoras' theorem on the left-hand side, big triangle. This is proposition 1.47, Pythagoras. And we've just said that AC and CE are equal, so this is 2AC, 2AC, cross AC. So similarly, we're going to do a very similar thing on the other side. Remember, we've got two triangles. We're going to repeat the arguments on both sides. We're going to get EF. That's the other hypotenuse cross EF. And this is equal to 2 times GF cross GF. Okay, and why is that? I guess GF and CD are the same, right? This is opposite sides of a parallelogram are equal. So I'm going to leave that out. This is actually, sorry, what I meant to say is GF is equal to CD. I gave the argument before I wrote the statement. So this is since GF is equal to CD by proposition 1.34, which says that opposite sides of a parallelogram are equal. So that's how this goes. And so more algebra, we're almost there. So now we're going to go and say add them up, right? EA cross EA plus EF cross EF. All right, we add them up, we're going to get 2 times AC cross AC plus CD cross CD. Okay, and now we're going to apply Pythagoras again, and to a different triangle this time. Remember, we spent some effort in proving that this triangle AEF, sorry, the angle AEF is a right angle, so we're going to use it now. So this is, the algebra, hence, up to this point, didn't use any of the geometrical proof, and now we're actually going to use what we did. we're gonna apply. So sorry, we're gonna go over a little bit. Hopefully, we won't cover too much. Proposition 1.47, which is Pythagoras, to the triangle AEF. Right? Remember, AEF is that triangle that we constructed with the right angle the top angle AEF, I guess that's the right angle. And we're going to write down what Pythagoras says, which is that AF cross AF, which is the hypotenuse, is equal to EF cross EF plus AE cross AE. Right, and this is actually what we just wrote down. So this is equal to 2 times AC cross AC plus CD cross CD. Right, so this is just in this term and, putting it there. And of course, now we have another triangle, the other right angle triangle. We're going to finally apply proposition 1.47 to the other triangle that's a right angle triangle, which is ADF, and get another algebraic relation, and that's going to be AD cross AD plus A. I think I wrote something wrong down in my notes, so let me go back to the diagram and fix it. So AF is still the one that we want because that's still the hypotenuse. All right, go back to the diagram, right? AF, now the triangle ADF. Why can't I click? All right, there we go. ADF, right? It's going to be F. It's going to be ADDF, right? So that's the other side. AD cross AD plus DF cross DF. And the conclusion follows because this thing here is not equal to this thing here. And that's essentially what the statement of the proposition says, right? AD cross AD is the A squared plus B squared is equal to twice of AC cross AC, which is the midpoint, right? Well, half of the whole line. And CD cross CD is the square of the difference of the equal and unequal parts. So that's it.
Nice. That was one of my favorite proofs so far.
Yeah, a bunch of algebra that maybe I could have written in a shorter way, but I guess that was nice. Just using Pythagoras to give us what we want.
Well, apart from that one corollary after Pythagoras, we haven't used it so far, so it's nice to see it actually get used.
Yeah, right. Is that right? We haven't used it yet. Huh.
I don't think so.
Because the corollary was 1 point. Are you referring to like the one right after?
The one right after it, yeah.
Oh, right. There we go.
I think, I'll just check, but I don't think we've used it in book 2 so far. No.
Yeah, I don't think we have, because I when I was going through the notes, I actually forgot the number. I thought it was 1.46. I'm like, oh no, it's 1.47. If we'd used it thus far, I would have corrected myself. So yeah, this is cool.
Yeah, I think it's also nice to note that before reading through Euclid, you might have thought that it took special genius to invent algebra, but like anybody who's working through this book is just like so sick and tired of writing down all this stuff that they're almost forced to invent algebra. Right?
Yeah, I'm surprised they didn't at that point. I mean, they certainly algebra came much later. I actually don't know what the historical roots are with using variables to represent, letters to represent variables.
Maybe it's close enough that we have lots of things like that, right? Where you get used to a certain mode of writing, and then something that's marginally better, you kind of just want to stick to the old way. So you could argue that it essentially is algebra. It's just got some English words instead of symbols, but it's not so different apart from missing subtraction or whatever. So maybe the The real step is to, when we think of algebra, we don't think of it just as a kind of way of writing down statements about things in the diagram. We tend to think of it as having an independent existence, right? Like those symbols live somewhere, and it's not just a way of writing things down, although it's also that. Maybe that is the step that you need to take. I don't know, but yeah, it's clearly latent here. A lot of the algebra.
Yeah.
I actually really like the way that the minus b appears in this statement. So if you were, as moderns, if we were writing this down, we'd put in a hypothesis. We'd say, A is bigger than b or something, right?
Right. Yeah.